I just forgot to share that one. Okay, let's start from the beginning. So, as I was saying the other day, we introduced the harmonic oscillator, and we know how to get these energies, and we went through the spin-orbit interaction, and thanks to the spin-orbit interaction, we managed to get this magic number 2 remains 2, 8 was okay, 20 was okay, but then the next magic number was 40, and 40 doesn't correspond to a nucleus which is particularly stable, right? But by adding the spin-orbit interaction, we have that these guys split into different levels, this building of protons and neutrons, and with the essence that we have these gaps, which corresponds to this particularly stable nuclei, because the gap is an energy gap. It takes a while from go to this floor to the next floor, right? And takes effort, energy to go from the whatever floor to the next floor. And here it doesn't take so much effort because the floors are close by. So you go upstairs, it's just around the corner, just up there, boom. You are 5 stairs, but here you have to climb a lot of stairs, so that you have this energy gap here, which makes this nuclei which fill up this last orbit or shell particularly stable, right? So these are the magic numbers, and they are reproduced once we introduce the spin-orbit interaction. This is a Wood-Saxon plus spin-orbit interaction, but we can also do the harmonic oscillator potential plus the spin-orbit interaction. One exercise was to apply the spin-orbit interaction to all these levels, to the 0s, and this becomes 0s 1/2, right? Because now remember that we use perturbation theory. And by using perturbation theory, we have to get the, let me see, the delta E, the perturbation of the harmonic oscillator potential was given by this NLJ, NLJ, MJ. Then actually there was an S also there. Then we have the spin-orbit interaction, which was LS. And we use this basis of states because they commute with these guys, right? They commute with these guys. And then the same thing here, NLS, JMJ. And this was the energy change, and we saw that for the 0s become now the 0s 1/2, because now we have to add these two quantum numbers, and this is equal to J, and there was no change in delta E. Delta E was equal to 0 for this particular case, and this was the harmonic oscillator potential, and this was the perturbation, which we call H prime, which is the harmonic oscillator potential, plus the perturbation. You know, this is the total, right? Let's call this total so that we don't confuse. And this is the perturbation, where this is equal to minus LS, right? But we saw that for the 0p, actually there were some difference, and then we have the one coming down and the one coming up, and this became the 0p 3/2 and the 0p 1/2, right? And with respect to this, there was a delta E here, right? That we calculated. And there was also a delta E here. Right. And so on and so forth, we built our building. Who is bothering with all these WhatsApp messages now? Do you have any questions or what? Hi, Nico. I'm not feeling well today, so I arranged Craig to collect the key from Chikalele. Okay. Okay, so Craig will open the PC lab. He will arrive soon enough, and he will do the tutorial. Okay. At 11 something. 4. All right. So that's it. And I'm going to close this WhatsApp nonsense. Otherwise, I get confused. So all right. So far, so good, right? So what is the class now? Why we are losing people? Anyway, so we have now a building for protons and for neutrons. And we have the 0s1/2. Now let's do it with the spin orbit interaction. We have the 0p3/2, the 0p1/2, and this is the magic number 2. This is magic number 8. And then here we have the 0d5/2. Then here we have the 1s1/2, and here we have the 0d3/2, right? This is for, let's say, for protons, magic number 20. We're going to focus on this one. Then you have the other ones here, the 28, actually the FP shell, but we're not going to go so high up. For the purpose of this exercise, we're just going to build our building. And remember that for neutrons, because the binding energy goes down, the neutrons will be a little bit more bound, but we'll have a similar building of levels, and with the 0s1/2, and then a little bit down here, the 0p3/2, 0p1/2, and then we have the 0d5/2, the 1s1/2, and the 0d3/2, and then we have the magic number 20, and then we have 28, and then we have something else, right? And this will be for neutrons. It's 8 and 2. So now what we want to do is to check the predictions of what we have here. And let's do, for instance, a nucleus like, let me see. What is my pencil? Yeah. So let's take a nucleus like, say, oxygen 17 with 8 protons and how many neutrons? 9, right? Okay. So now we are going to check the prediction. What does the shell model predict for the ground state and first excitations of oxygen 17 as an example, right? Easy case. So what we do now is we fill it up. We fill up the building according to the Pauli principle, right? So we say, okay, here we have these two guys, 1 and 2, right? Remember, the occupancy goes as 2J plus 1, right? Remember that. The occupancy, according to the Pauli principle, will go as 2J plus 1. And remember, we investigated that by having different particles with the same angular momentum orbiting in different ways. So basically, those were the magnetic substates, which have this the total occupancy for each floor in the shell model building. Then we say that this was 4, 2J plus 1, 2 times 3/2 is 3 plus 1, 4, 1, 2, 3, 4. Then here's also 1/2, 2. And that's for 8 here, right? And now we need 9, and we keep building 1, 2, 3, 4, 6, 7, 8, and one particle here, 9. Right? So now we're going to see what the experimental data tells us. We're going to go here, and we're going to our NNDC data, the data evaluation, NNDC. And there we're going to, I'm going to make this bigger so we can see things nicely. And we're going to go to the chart. And in this nuclear chart, we're going to go to oxygen 17 and see what is the ground state. So oxygen 17 is here, actually. You just click there. And we go down here and we check the level scheme. Yeah. So basically the level scheme is telling us what is the ground state. It's a 5½ plus. But that's probably not. Let's make it list of levels so it's easier, it's neater. So, but the ground state, as you can see, is a 5½ plus, right? So it's a stable nucleus with a 5½ plus ground state. So now we go and see what is happening in our shell model. So this is our J. And this is the odd particle, right? So the odd particle actually is giving the information about, all these guys couple. Actually, there's something called the pairing force, the pairing interaction. All these guys, generally, they couple. And they couple to J equals 0, right? Because you have spin up, spin down, right? All of them are spin up, spin down. And they couple to J equals 0. So the odd particle here, this odd particle characterize the properties of the nucleus, in particular oxygen 17. As you can see, we went to the NNDC, and the ground state is a 5½ plus. Here, you see. And as we know also, the parity is equal to the -1 to the L, and in this case is D, so it's 0 is S, right? 1 is P, 2 is D, S, D, P, F, G, 3, 4, and so on and so forth, right? So the D is obviously even, so the parity will be positive. So that's why if we compare this with the experimental data, we see that the ground state of oxygen 17 with 8 protons and 9 neutrons is a 5½ plus. Ground state is 0. Reference energy 0, not real energy. The real energy of this level, I'm going to say this because it will be a clear misunderstanding. I don't want this to be a mistake in the test. This actually is the binding energy of oxygen 17. What is the energy of this level? Right. And the binding energy is equal to the minus energy. So you need to calculate the binding energy of oxygen 17 to know what is the energy of this level, of the ground state. So this is the ground state, right? But you must know that we just call it 0 because we are going to refer everything with respect to the ground state. So then, by looking at our building according to the Pauli principle, tell me, Sayalo.
Okay, I can see that you are here. We are saying the parity will be positive.
Right.
So
the parity is positive because the D is 2, right? So yes, this odd particle is in the D, right?
Then if N is 2, then L is supposed to be from 0 to 1.
No. This is just a one number. So if you have D, you have count 0, 1, 2. There's nothing to do with transition probability. We're going to go through that later. So the transition, that's one thing is the decay. We're just talking about the level. The decay, we have an electromagnetic transition, and then that's going to be from 0 to 2 or whatever it is, right? But that's what we're going to investigate in a little bit. Once we identify what is the angular momentum and parity of the first excitation. This was the ground state, and then the first excitation in oxygen 17, it is what? That's my next question. And if we look here, we see that this particle, right? This particle can jump down here. That's the easiest jump because it's close by in energy. So this particle move from here to there, right? And then it will move from a 5/2 plus to a 1/2 plus, because S is equal to 0, right? Also positive. So now we look at the NNDC and see what happened. So the first excitation is indeed a 1/2 plus, right? And so we can explain also the first excitation in oxygen 17, which now is not a question mark anymore, but our simple model is predicting that it's a 1/2 plus. So now comes a little more complicated situation at a higher energy, where the second excitation is, according to the NNDC, is a 1/2 minus, right? So now we can play around with the shell model. And you see, let's go to the energies. It's quite high energy. This was 870 keV with respect to the ground state, 870. But then suddenly there's a big jump in energy. You know, the next one is 3055, right? 3.055 MeV or 3055 keV, right? And it tells us that this energy, it has a 1/2 minus. So obviously, this is a hint of what we need to we require more energy for this 1/2 minus state equal J parity, 1/2 minus state to be excited. And later on, we go through the multipolarities. But right now, we just want to make sure that we know what is the total angular momentum for each of the states and how can we explain it according to the shell model. So we have built our shell model. We have put every inhabitant, every proton and neutron in its flow, on its particular flow according to the Pauli principle. And now we just have this guy, we moves here. But, you know, now how do we produce a 1/2 minus? You know, this guy is quite interesting because it requires quite a lot of energy and it's a 1/2 minus. So my question to the class is, how do we produce a 1/2 minus? Let's write things here so we don't get confused. Let's go move to only to the neutron side. And we're going to make 2 here, and we have 2 here, 4 here, right? And here we have another 1. So we are going to 2 more here. So basically 0 as 1/2, 0p 3/2, 0p 1/2, 0d 5/2, 1s 1/2, and 0d 3/2. So this is oxygen 17 for the neutron side, right? So how do we produce? How do we make this guy here? How do we make 1/2 minus? Manfred, what do you think? How do we produce a 1/2 minus? Remember, the parity is equal -1 to the L, right? This is L, and this is J. This is energy. So, Manfred, what do you think? How do we make this excitation here? This one. Huh? How do we make this guy here? Any ideas, Manfred? Ganinchuti, what do you think?
Can you please repeat the question? I was going to check if anyone is there in the so I missed your question.
Okay. So my question is: we have gone through the nuclear data tables, and this is the evaluation for oxygen 17, and we know that the ground state is of J pi 5½ plus. The first excitation is at 870 keV energy here, and it's a 1/2 plus. And the next excitation is a much higher energy, 3.055, is a 1/2 minus. So the 5½ plus, we interpret it as this particle jumping from here to there, right? This particle jumped from here to there. So originally it was in the 5½ plus and it goes to the 1/2 plus, right? So that's how we explain these fellows here. 5½ plus was the ground state as the particle was right there. And then it moved up there by jumping to the next flow, right? It needed some excitation energy to go down there, up there. So now we want to explain this. Why do we have a 1/2 minus as the next excitation? Now I'm going to go back so I don't confuse you in what we're going to do next. So my question is why the second excitation is a J pi equal 1/2 minus.
In which subshell, Prof?
You understand the question, Ganinchuti?
Yeah, so why? Because we have yes. I think okay, so since parity is negative,
It's negative. It's negative. Remember, another hint is that all these guys, they always couple to J equal to 0, right?
Yeah. So I guess the reason for a second excitation is because of no, there is something called it magnet. Like I forget that name, but it goes with dipole moment, something like that. Second dipole moment.
Simple than that. Much simpler than that.
No. Okay.
You need to play with this combination. This is your building. So basically, you have to look at these inhabitants and see how they're going to make a 1/2 minus. How these guys are going to rearrange themselves, and how by obeying, always the rule is to obey the Pauli principle, how they're going to make a 1/2 minus state. Leeds, you say something? Jafta?
No, Prof, I wanted to ask in which sub level is this J minus half minus?
But this is what you have to do, Cialo. This is what I'm asking you. You need to figure out how this comes into place. You see? I'm asking you that question. Why this 1/2 minus is happening? Leeds, any idea? Manfred, any idea? Do you have any idea now?
Why? And I think I put the idea.
You have to think what can we do here to have, it's like a little puzzle, right? What can we do here to make, I told you this guy by itself gave us the ground state, right? Because the particle was staying here. The jump gave us the next 1/2 plus, because S is equal to 0, right? 1/2 plus. So now we're asking, how do we produce the 1/2 minus? So this guy is by itself. Any ideas, Manfred? Is Manfred there? Manfred,
Manfred just get to PC level now.
Okay. So obviously the only 1/2, what is the 1/2 minus here? Is this P. The P is the only, out of all these orbitals, right? The D, the S, the D, the S, they will give us L equal 0, 1, 2, 3. So the S and the D will give us even number, right? So they will give us positive parity. So it's only the P which can give us a negative parity, right? So what happens here is very easy. So we break a pair, and this particle gets promoted there, and they couple to J equals 0. And the remaining particle, which is this one here, there was a remaining particle. This particle move up, right? This guy moving up and couple here to J equals 0. So now the odd particle stays here. So then,
Prof,
tell me.
Is it because of P is odd parity, right?
But that's what I just explained it. You came 5 seconds too late. So now the P is negative. So the only particle, the remaining particle here is 1/2 minus, right? So this is the process, most likely process that happened in this, to make a 1/2 minus, is that this pair, which was here in the P 1/2, broke. And for that, you require energy. That's why this energy is high, right? This 3 something MeV. Not only that, but also you have to break the pair and you have to go up there, right? So then you produce a new pair here, which couples to J equals 0. And then the odd particle is now this one. These are the odd particle, and which lies in the 1/2, because P is equal to 1, right? And this negative parity, 1/2 minus. And this is the understanding of this particular excitation in oxygen 17. These are single particle excitations, but in general, in quantum mechanics, there's no such a thing. But whenever we have a state, say 2, 0 plus and 2 plus, or whatever, 2 plus will always be a general combination of different wave functions, which in this case, they will be the different orbits, or so many percentage of the particle to be in the P 3/2, the percentage to be in the particle in the beta in the 0P 1/2, and so on and so forth. There will be a percentage, a linear combination of possibilities, which will describe these 2 plus. There's not just the 2 plus, or even these guys, is not just a single situation, but there's always a linear combination of different possibilities, where the larger probability are these ones here, what we are talking about. Okay, so now our task will be to go to a different nucleus, and we are going to open a new page. But in the meantime, here, we're going to go to another nucleus, which is, let's say, oxygen, this one, fluorine 17. Fluorine 17, as you can see, again, the ground state is 5½ plus. Let's see what they say. So fluorine 17 is 9 protons. And you can see the same situation here. 9½ plus, 5½ plus, 1½ plus, 1½ minus. Again, similar energies, right? This is a nucleus which is different to oxygen 17, but it behaves very similar, because the buildings for protons and neutrons, as we always say, is similar. It's similar in the sense that now we have fluorine 17. Sorry, that's oxygen 17, but fluorine 17 is a very similar nucleus where you have 9 and 8 instead of 8 and 9, right? And similarly, as we have 4 oxygen, we will have a 5½ plus here, 5½ plus there. Then we have a 1½ plus here, 1½ plus there. And at much higher energy, we have a 1½ minus and a 1½ minus, right? We see the same situation. And this, as we know, arises from the same fact that we have the same kind of building for protons and neutrons. The shell model building is the same, with only the difference that these guys are a little bit more bound for neutrons than for protons. And the same thing happens here. So basically, instead of having 8 here, now we have 9. 1, 2. So the odd particle basically, in the case of 17 fluorine, the odd particle is here on the proton side, whereas for the case of the sorry, let's do it. Yeah, for the case of the oxygen, we have these guys were full, and the odd particle was on the neutron side, right? So as you can see, the energy, the excitations are very similar. 5½ 1½ 1 minus at 3.1 MeV. The other one was 3055. Very similar excitation energies, and this is also a property of the shell model, but also a property of isospin symmetry. Where similar nuclei with the exchange proton and neutrons. As you can see, the same kind of nuclei. These are mirror nuclei. When you exchange the number of protons, the number of neutrons, they present very similar properties, right? And now let's go to what you were mentioning before, because this is also part of the question. Is now what kind of, you excite the nucleus by any means, and what kind of radiation do we have here? Nucleus always try to de-excite from the excitation down here. What is this excitation, guys? What is this? What is the radiation? J initial plus minus J final in absolute values, less or equal lambda multipolarity, less or equal J initial plus J final. So what is this? Cielo, what is this transition here? What is this electromagnetic radiation?
I think it's multipolarity.
Multipolarity what? Cielo, I'm afraid that you're not going to pass this course. So we need to get this one, which was an exercise that we did a couple of weeks ago. Jafta, Leeds, what do you think?
Which one, Prof? Maybe I did not hear the question properly.
What is the multipolarity of this transition here?
Which transition?
This one I'm drawing on the screen. This one? This 1½ plus decays to 5½ plus. What is that multipolarity?
Oh, okay. I think we can use that formula to calculate it.
I also think so, but I want you to give me an answer.
Oh,
I don't want you to tell me what I know. I want you to tell me an answer. Jafta, what do you think? What is this radiation here? Leads? Leads, you're not talking at all. What do you think?
Sir,
Kaninchuti?
could be maybe 2 and 3, right?
So 5/2 minus 1/2 is how much?
That is 2.
2.
In absolute value, yeah.
And this guy is 3, right?
So it's 2 and 3.
Right. But then what is this? So there's no change in parity. So we start with, what do we start? E0, M1, E2, M3. So 0, 1, 2, 3. As I say, according to the Taylor expansion, once we have an electric, the magnetic doesn't come out. So basically, this transition is 0, is between 2 and 3. So the 3 won't be there. So it's going to be just 2, E2. Right? Because it doesn't reach the 1 or the 0. Right? It's not M1. Whenever you have an E2, M3, then 3 is much weaker. So it's only E2 what remains. So this transition is an E2 radiation. What about this one? Leads, Jafta, what is this transition here? What is Leads? Is Leads in the class or no? Leads, are you there? I assume you're not here, Leads. It's very important that we get a mark for interaction, for answering questions, you know. Saringuti, what do you think? Anishuti, what do you think about this one? Oh, Manfred, ask Manfred, what is this transition here?
Manfred, answer.
Isn't E1?
E1, that one.
It is E1, right? Because 1/2 minus 1/2 is 0. 1/2 plus 1/2 is 1. And there's a change of parity. So we start from M0, E1, right? M0 doesn't exist because there's no magnetic charges. No one has found a magnetic monopole because that will imply that you don't have a positive and a negative, a north and a south pole in the magnet, but you have like a charge, a magnetic charge which doesn't exist. So no one has ever found a magnetic monopole. So basically, it's just an E1 transition. The same thing here. This is E1 and this is E2. Right? So these are the things that I'm going to ask you. You know, you're going to interpret, you know, you're going to apply the shell model, you're going to put the inhabitants, the proton and the neutrons where they belong, according to the Pauli principle, and they're going to see what kind of total angular momentum, what kind of parity, and what kind of radiation we have, right? So now we have a very simple model which can explain these things, you know, quite easily. Let's move on and let's see what happened with the oxygen 19. Let's go back there, oxygen 19, which is 8 and 11, right? So oxygen 19, we have, let's go to the, this one is all coupled to J equal to 0, the protons. Let's go to the neutron side. So again, 0 as 1/2, 0p 3/2, 0p 1/2, 0d 5/2, 1s 1/2, and 0d 3/2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 11. 10, 11. Okay. So again, this guy is coupled to J equals 0. So this guy is the odd particle. So according to this, the first excitation should again be 5/2, right? Let's look at it, and then because we don't trust anything until we compare with data, and then here we go, and we put here 19 oxygen, and let's see what happened. 19 oxygen again, 5/2 plus, boom, done. So the next level actually is a 3/2 plus, and the next one is 5½ plus. So it seems like it goes, the particle may go from here to here, then here to here. So, which, you know, it will be easier, it will be less energy to come here than to come here. But there may be other combinations happening and making the 0d 3½ a much easier solution. Or it may happen actually that this nucleus start becoming deformed. Remember, very important to remember is that for these guys, we have used the harmonic oscillator potential, and the harmonic oscillator potential is 1k of r squared, and these are present a spherical symmetry, right, for each point in the sphere. So this study that we are doing is good for spherical nuclei. If the nucleus is not spherical anymore and there's some kind of deformation, deviations will happen. So like in oxygen 19, we are fine here. And then we get this guy, which requires more energy really than this guy, right? The next excitation, according to the shell model, will be a 1½ plus. And the next one will be maybe a 3½ plus, and then something negative, because also we can break these pairs or whatever, right? But what we see is that really this is a 3½ and this is a 1½ right? So suddenly something is happening, and we go back to the limitation of our shell model, which is that is valid for spherical nuclei. And now let's move on and see what happened with neon 21. Say, let's keep going inside, close, farther away from the magic numbers, right? And we keep playing, and this is the way we learn. We keep playing and see what happened with 20. We want to make the shell model fail, because when we fail, we see that there's some other physics that we are not considering, right? We make it fail. So let's see, and we make it fail already. Let's see, the 3½ 5½ neon 21. Neon 21 is 10 protons and 11 neutrons. So the neutrons, the protons will be 1, 2, we know 1, 2, 3, 4, 1, 2, and then we have 6, 7, 8, 9, 10, right? And 8, actually too many. 4, 8, 10, right? This would be a magic gap here and a magic gap there, which I didn't do it very nicely. So let's make it now nicely. And here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 10 protons, 11 neutrons. And this should be the T5½, right? So according to our shell model, to the spherical shell model, the neon 21 nucleus should have a first excitation, a 5½ plus, and the next one will be this one guy coming here at 0, actually a 1s 1/2, and then this particle moving up there, maybe 0d 5½ 3½. So then here we should have a 1½ plus instead of 1½ plus, right? But what we see, this is the shell model prediction. Shell model prediction. But what we see is not that, but in truly what the NNDC says, 21 neon, the data, the actual data, say that the ground state is actually, you see, the ground state is a 3½, and then there's a 5½ plus, right? So 3½, and then there's a 5½ plus. So these guys, they are not showing what the shell model prediction is giving, right? So there's a big question mark here of what's going on. And this is why we need to know the weakness of the shell model. And again, what is the transition here, guys? What is the transition here is something that you need to investigate. In this case, will be an M1 E2, right? But in this case will be an E2. So, but anyway, there's something fishy here. There's something fishy that I want to leave it now. For the next lecture, I want you to come with solutions. I'm going to give you the whole weekend to understand the problem of Neon 21, right? And why suddenly the shell model is failing. Our prediction is not so good anymore. There must be a reason for that, right? And then actually, I want also you guys to put yourself problems and say, okay, say if we have any nucleus in the chart, if we go here to the chart, back to the chart here. And then we take any of these guys, phosphoron 28, any, we're not going to take odd because the situation is more complicated, but you're going to take any odd even nucleus, okay, like we have done so far. So sulfur, let's say sulfur 29. Sulfur 29. Ground state J half plus, sulfur 29. So I want you to go to sulfur 29, be able to draw your building. 29 sulfur, just an example, right? 29 sulfur is how many? 16 protons. And here you have 13 neutrons, right? So according to the shell model, there will be 1, 2, 1, 2. I want you to build your own level scheme, 1, 2, 3, and go back here and say, okay, 1, 2, 1, 2, J couple to J equals 0, these guys, according to the pairing interaction, 8, 9, 10, 11, 12, 13, 14, because the D, if I have, they can take 6, 14, 15, and 16. Okay. Now here the 13, 1, 2, 1, 2, 3, 4, 8, 9, 10, 11, 12, 13. Right. So 13. So it is a 5½ plus. Still we're in the 5½ plus. And that's kind of what the prediction, this is the 0 D if I have, right? And we can go back here and investigate what is the list of levels. If 5½ plus is the is not found, that one, that's probably not, it's a very exotic nucleus. So let's go to sulfur 31. Yeah, let's go to sulfur 31. See, sulfur 31. List of levels. So 31, let's make it this 31. So it will have 31 here. Let's remove this one. Let's make it 31. So this guy will be 13, 14, 15, right? So 1, 2, 3, 4, 5, 6, another 6 here. We fill it up, and then we have the odd particle will be here in the 1s 1/2. And the 1/2 is a J pi equal 1/2 plus, which is what we see for the sulfur 31, right? 1/2 plus. And then it goes to the next level, which is a 3½ plus. So for whatever reasons, Now we're going to investigate further. Remember, this was the 0d 3/2. This particle jumped there, and this is the first excitation. So by exciting this single particle to different levels, we can actually build up that we have a 1/2 plus for sulfur 31, and the next level is a 3/2 plus. What happened up there is a combination of these two and more, so it's more difficult to predict with this simple picture. So now our job is to be comfortable and go even farther, even farther. Let's say sulfur 31. Let's go to the level scheme here, and let's go to anything. Let's say vanadium, titanium 53. Let's see whether you can make it titanium 53 and investigate what are the levels on titanium 53. It's a tentative 3/2 minus because it's quite exotic. Let's go to argon 41. Argon 41 is a 7/2 minus. So basically, let's not go too far from the stability, so we don't get into. So argon 38, no, argon. See, argon 37 is a 3/2 plus. So you build up. Argon 37 is 16 protons, and again you do the same thing. You build up your building. You build up your building and check what kind of electromagnetic radiation. Investigate what is J, what is pi, and the electromagnetic radiation, the exciting those levels, right? So this is what I want you to do throughout the weekend, to have a beautiful idea of how you put all these protons and neutrons into different levels, into different excitations, and how do they characterize the properties of nuclei just by looking at the simple shell model.